Hello everyone. Good morning. It's the who's in charge over there? Is the stream like going? Can I start? I guess. Yes. Okay. Good. Then, so again, I am Agustin Gutierrez. This is our third lecture in the second week of the final class. This is my fourth favorite model and edition, of course. And okay, what do we have for today? Actually, first, since it's early as a reward for all of those of you who come here early, let's just do a short commentary on one of yesterday contest problem, and then which I think is, well, it might be distantly related to the class, but not really too much related. Everything is connected to everything. And then we'll start with the properties. Okay. So first of all, any comments on yesterday contest, like especially if like the default quality was way off, you think, or there was something very bad with the problem. I got feedback that there were many technical issues with the bike junction, something judge. They wanted that start bike, something like that. So I try to avoid that one, but it's always like when one judge starts working, the other one breaks, and it's tricky that process. We'll try. Any comments? Okay, no, nobody's.
Yes.
Yes, comment here. Perfect.
Yes. Some of the problems didn't include that.
I see. Yeah, that is not ideal because since many years now, probably around 10, that is always included in ICPC, and that might happen again, basically. Sorry about that. But I still, anyway, I try to change with the source of some problems, but some problems might still be from, let's say, many years ago, which has the advantage that you are less likely to know them if they are very old. Let's just say call those problems very old. But a disadvantage is that yes, like the style of the competition changes different ways. Like some very very old problems have very very different style and are not even very suitable like for practice. But problems from like 20 years ago, you find many very nice problems. But it used to be the case even in the regionals of ICPC and the world finals of ICPC that it was just like that. You were not even told what the time limit was. Maybe 1 second or 20. But since you didn't know how many test cases there were, it didn't change too much, right? So it was a bit of guesswork. But the usual, so if you face something like that, you basically should assume, which is what we did, like, okay, if I can handle one test case more or less fast, then this should be okay. So a 1 million n will still not work quadratic time. And if you have 1000 n and you do quadratic, it will be very surprising if then there's a million test cases, and that's why it's not accepted, like it's unusual. So even though it's not specified, it's usually more or less reasonable. Still, because all of the tests go together, and there is some unspecified factor there, it is a good idea to optimize for the total and not the worst single test case because they are run together. So, like if you can do some pre-computation and then answer everything quickly, it makes a lot of sense to do that, right? Some problems maybe require doing that. That was like the idea, even though it's not specified exactly how many test cases there are. But for most problems, it doesn't change too much. It's just unusual, yes, I understand, because now if you look at the past 10 years, I think it's always specified, right? I think that's a good change, actually. But I cannot go and fix the previous problems, and I still want to use them, so sorry about that. It's a good question, because that way we align expectation. Now you know what to do, basically. Keep solving. Okay, any other question or comment? Yes.
But in problem 8, the hardest part for it from my team.
Oh, right, that's the one I will talk about now.
Yes. Okay, but we could not truly like solve the time limit. was like the hardest part for us. Was seeing that it was 20 seconds instead of 2. I don't know how to make it better. But yeah, it's just
I'm not sure I understood
the time limit
the
of
main
the problem
problem.
was
Yes.
20 seconds. But it is kind of hard to see because it gives in milliseconds. So it is like 20,000 milliseconds. And
Oh.
by default, we assumed it was 2.
I see. I'm not familiar with the details of that, and it might even be related to the VJudge, how it
Yeah.
presents versus the original one, so there might be even more complicated interaction there. So yeah, sorry about that.
No, it's
I think there were people who were not so far from the time limit because they were optimizing a lot their algorithm, but the actual intended one runs much faster. So in a sense, they were far away from the expected ones, but because the time limit was somewhat generous, okay, they are close. It looks close, but it's not that close. Okay, difficulty-wise and topic-wise, was it okay? Yeah, there were a few problems that it's debatable whether it makes sense to put something that hard yesterday, but I wanted to mention them today. So basically, that's why they were there. Okay, and also you can check them for practice, right? Good for us. Okay, then let's move on to commentary on problem 8. Many people were asking me about this problem fence yesterday, and actually it looks like it was mentioned just now again, so there seems to be quite interest in that one. So I said I would mention about this problem briefly, and a little bit of story. And so this problem, the source, I don't know if you checked it, or if you usually check the source of problems in contexts like this. Sometimes the source of the problem is random and not very curious, but this one is for round 3 of Google Code Jam, year 2010, right? So I'm very fond of this round and this problem because it's the one and only time that I qualified to the Code Jam finals, right? So this was a critical, I think this one was the critical problem, so I did good on this one, so I was happy. So basically, what was this problem about? It's essentially an abstract variation, so the problem gives you many numbers, which you can add, so you have infinite copies if you want every number, and you want to add up to a certain target, right? A goal. There is an objective number that you're aiming for, and you want to use it as a few numbers as possible. So it's a standard knapsack where these are the weights. You have infinite copies of every object. This is the knapsack capacity, which actually in this variant you want to completely fill, right? And it is important. It's not a variation where you can leave extra space. And the value of the objects is very particular. It's 1 for each of them. Sorry, it's minus 1 basically, the value, right? So the cost is 1, so you want the minimum number of objects, right? So it's almost like subset sum, but you care a bit on the cost, like everything costs 1. So this is a very peculiar problem because there is an unusual property here that I know very few problems. I know a few problems that are based on this restriction, but very few that I can remember. This is one of the most interesting to me. You have to use this bound that the target is very large, right? This number is arbitrary by itself, right? The point is that this is, all of these numbers were up to 10 to the power of thing, I think. So this is about quadratic in the numbers. That would be the important order of magnitude and sizes when you analyze it. Right? This problem is not really, well, maybe it is solvable, I know, but it becomes much harder if you drop this restriction. So it is useful to know that the target is very big. If you see it and you trust that this is not just random added constraint just because, and you might want to use that constraint actually, well, intuitively, I I think that it is quite intuitive to say, okay, since the target is so large, then I am very far away compared to the numbers magnitude from target. So at some point, I will want to cross a huge gap quickly, and so I will want to use many copies of the largest element I have, whatever it is, to get there quickly. And maybe add a little bit of the other ones, like to fix the situation. But because if this is so big, this will interfere a little. That is the intuition. And you can actually do that, because if you're currently at number x, and you happen, and t minus x, let's call this one the maximum, and t minus x happens to divide, and m happens to divide t minus x, right? That is the remaining value that you have to add is a multiple of m. So I want to create a multiple of m, basically. Whenever you want to create a multiple of m, it is very clear that you just have to use that largest element exactly the remaining value, right? T minus x divided by m copies of m, right? I mean, if you have already used some elements and your current sum is x, and this happens to exactly be divided by m, then it is clear that for the remainder you just want to use copies of m. Right? So this would be the full solution. So in a sense, you want to, using as few extra detailed cost as possible, arrive at a number with the same congruence as t, right? Basically, if we think in terms of how much do I still need to add, well, you want to get to a multiple of m, right? As quickly as possible. And you can formalize that intuition fully and get the solution, basically, by actually creating a graph which has one node per modulo, class modulo m. Let's say m would be 6 in this particular drawing, right? So you can intuitively think that the node where you are represents the congruence modulo m of what still you need to add. So initially it would be t modulo m. Let's say it's 2. This is t m, whatever it is. This is where you start. And every time you add an element to your solution, well, you would subtract, right? If I add a number 1, then 1 less is to remember, so I would be allowed to move from class 2 modulo m to class 1 modulo m, right? And since that movement means that I add an element, this would have a cost of 1 element, right? That is the intuitive idea. So now I can add edges, a lot of edges, modeling, adding elements like this, right? And the only extra detail that this is cyclic because this is modular. So for example, if I'm at from position 2, if I have an element like 4, well, I subtract and I will get to, well, m minus 2. Let's say that this goes that way. Something like 2 here. Well, this one would normally have a cost of 1, but if we look carefully, we have crossed like a border modulo m. Actually, that implies that we will need 1 less copy in the final version. Right? Let's say here m is 6, so let's say our target was 32. So if I get to modulo 0, which is my target, right, to get to a multiple, I will get to 30 actually, and so need 5 extra copies in the end. Right? But if I place a number like 4, I will move to 28. So now the next possible multiple I can arrive at is 25, which will only be 5 extra copies at the very end to complete, not 6. right? Every time I cross, okay, I have added a number, but I have also saved one extra copy in the final adjustment, right? So the net, that means that the net cost is 0 when we cross, right, the border, right? And if you do this, all that I want is a minimum path from the start to from the starting modulo to the 0 modulo, right? I want to, as quickly as possible, get to the multiple, and then it is obvious that if I have arrived at a multiple, then for the rest, I clearly just need to fill the top. Is the explanation clear? This is basically the thing. Of course, you will not build this graph in memory. That would be quite bad practice. It would be analogous to having a grid or character that walks the grid and something like that, and actually creating a vector of the adjacent list and such. You just need to, at every node, be able to know what the next edges are, right? Here it's the same. You would not want to add all of those edges. From one node, you can iterate very quickly and very efficiently and do what you need to do over there. It can even be optimized further, but if you are a bit careful with this, I think no powerful optimization, let's call them, are needed. Okay, so this is the key idea. Because this will reduce the space of possibilities here compared to a more direct approach. So why is this restriction needed, right? Because I have never mentioned it, right? Well, if the number t were smaller, the problem with this solution is that it would actually get to negative territory, right? We might do this, and perhaps, let's say, maybe let's say my target is a small number, right? So after doing this, it can happen that the minimum path is such that if I trace the minimum path and add what numbers I have used, the solution is actually represents something like, okay, start putting numbers, subtract it, and then you arrive at minus 18, let's say. That is a multiple of 6. So now you complete with minus 3 copies of the number 6, which subtract at the very end, right? Well, this would be optimal if this would be allowed, but this is completely illegal, right? This does not model the true problem. You cannot now use negative copies of the element as subtract to the total. That is not allowed. So if this happens to create a minimum path that does not go into negative territory, then it is clearly the minimum, because you will have to arrive here somehow in the true solution, and this is the mean path, so it cannot be repeated, right? But it could be invalid. But if this is big enough, basically, since a minimum path has at most this number of edges, right, m edges, and edges as 0, 1, you can then do some calculation. I think if this is more than m squared, more or less, you are sure that you won't get into negative territory, so this bound actually becomes a correct solution. Right? So in a sense, this problem is very hard for t between m and m squared, basically. That is like the hardest territory, let's say. Okay, is it all clear? Any question? I hope those that did not solve it yesterday and now have solved it very effectively. So I mentioned this problem was a lucky problem for me because at this round, which is the one and only time I qualified to such a final, there were 25 spots and I got spot 25, so very lucky borderline. I actually did quite slow the problem A at that one. Every problem had a small and a large. And then I happened to do this one relatively quickly, which was like the saving point, I guess, both small and large. Large version is this one, the one that you saw yesterday. And then at this point, I had a lucky guess of strategy, and I said, like, okay, problems are probably very hard, even before reading them, because this is round 3. I will just read this one and do the small one as fast as I can, which is usually some brute force or something obvious, and the same for T, and not even think about it. I did that. And luckily, since I did all of that without wrong answers, I qualified in the board, which I would not have if I had thought more about this problem. It was quite I like to guess. So I have good memories. Which is to say, unfortunately, there's not like a famous single judge where all of the Cochrane problems are very well ordered. There might be some place where all of them are. So this one apparently has it, but I think it is not extremely well known and published. So now let's make it more well known and published. Because there are great problems, I think, to practice in all the contexts, but in particular in Cochrane context. Those were very high quality in my personal experience and opinion. Not because of this problem, because of the problems in general, especially interactive problems. That's very, very interesting times. So put your coach to work and make your coach, your professional coach, actually work on reading all the problems and selecting the best and creating a contest for you. You should use your coaches. Okay. Any question on this one? I think that's all. Good problem. Good. Because I mentioned your coach because, of course, if you go and read many problems to choose which seems the best, then you cannot do a contest simulation, right? You have already done everything before it breaks the point. Okay. Then let's now go to the actual class. Let's now start with the proper lecture of today and wish for the best and hope that we manage to do it in time. Let's see. Okay. So what is today's topic? Today's surprise topic. I would say that today's topic would have to be linear programming. So who knows what linear programming is? I think a little more than half. Okay, we will explain it now anyway. But actually, I think the most important or most interesting, I hope, at least I hope, thing that I will focus on today is on linear programming duality, actually, both. Who knows what linear programming duality is and things that understand it well? Okay, I think this is less people, but not like 10% of people. No, still many people. Okay, good. I hope we can learn a lot. And so this might be a formal name for the lesson. Then a more informal notion, we could say that today's lesson is about LP, linear programming, without using or knowing simplex. So we will not learn or use or have to know simplex at any point of today's lesson. In a sense, my aim today is to learn as much useful ideas about linear programming as possible without simplex, right? And hopefully some of these ideas are useful for problem solving, even without having simplex in our notebook and without knowing simplex. Right? Simplex is the most well known, right? Not algorithm, but any general algorithm that solves the general linear programming problem. Right? Doesn't matter that it is simplex in particular. Okay. So let's start. And actually, I will do this side story again because I do not want to later have to do the side step to speak about a side problem because I need it. So I will mention it now because this might be useful later. I will mention, I don't know what to call it, but it is a well-known problem. Let's say the inequality problem. That is very general and almost like linear programming. Let's call it two variables. Okay, this is like two variables inequality problem. But this is a very specific problem. Okay, what is this problem? I guess some of you must for sure know about this and have at some point used this trick and know how to solve it. Let's say that I have n variables, right? x1 up to n, right? And I have m, right? Suspiciously like the number of nodes and edges in a graph. And I have m restrictions, right? And every single restriction has this particular form. Let's just say that it's, this j and I would not always be the same. So for the kth restriction, let's say it will have jk and ik, but the important thing is that each restriction will have two variables mentioned, and each subtraction will be taken, and that has to be lower than a certain value. Let's say lk, right? And you want to basically know if this can be solved, right? Let's say this has to take real values, right? So x as a vector belongs to real coordinates, right? But if everything is integers, in this case, it's not hard to believe that it has to be an integer solution if there is one, which might be a pattern that we will do again. So, have you seen this problem before? We want to know if this is possible to solve, if there is some some assignment to the variables that satisfy all of the restrictions, if they happen to be like this. And if there is some way to satisfy it, I would like to know how, right? Construct some solution. I am sure some of you know how to solve this because this is well known. And you are very good contestants. But I guess not everyone does. Okay. Any idea or keywords on how to solve this? Well, no. Okay. Actually, minimum path, basically. But in the most general case, Bellman further was quite nice for this. The key observation is that because you only case have two, this might be like a very common fundamental concept, right? If something in your problem always has two of something else, then the first something might be edges, because they always have two of something else, and the something else might be nodes. And that might be a helpful way to model it, because suddenly a graph has a couple, and we like graphs. And this is the case. I have a lot of restriction, but for every restriction, I happen to have two of variables. So that's pointing it, okay, number two has appeared. So these are edges and the variables are nodes. And this is very useful here. That is how to solve it and understand this problem very well. You put one node per variable, and then to encode this as a graph, every restriction now, let's say it points from the negative one to the positive one, the one that appears in a minus. So this wasn't good. If our restriction is like x4 minus x2 lower or equal than 10, I can model that as an edge from 2 to 10 to 4. And naturally, since I have one more number lying around, I can just write it there and see what I need to model. And the very nice thing about this is that in this problem, a path makes sense. It's something meaningful. Because a path will lead to equations like, inequations like, sorry, the other way. This is the edge from 2 to 4, and then if I have the edge from 4 to 3, it will be something like this. This is lower or equal than the first leg, and this is lower or equal than the second leg. So if I add a lot of inequalities in a path, in sequence, forming a path, what did I be doing correct? No, this is correct. For each edge, the previous one ended when this one begins, so we have cancellation, right? And even if this was longer, everything cancels except the beginning and the end. So it ends up, by simply adding the inequalities, whenever I have a path, I see that it works as if it were a single long restriction that goes from the beginning to the end with the corresponding sum. Right? So this is what makes paths so useful in this case. This is not necessarily for minimum path. This is for any path. Anytime you have a path, you can imagine that you have like done some closure and you have all of the transitive implied restrictions automatically because it works nicely. Right? So this would mean that I know that x3 minus x2 has to be less than or equal to 30 just by looking at it. Right? So this might lead us to notice, oh, paths are important, so I might use some minimum path algorithm and see what happens. Right? Which is an interesting pattern. And that happens to try to work and be useful. Okay? Someone mentioned Bellman fold, and another way to maybe guess that it will be useful is noticing that in this particular problem, if I do this with a cycle, then I will have a path from the beginning to the end, so from a node to itself. So it will be like x minus x, the final result, and it also cancels out. So if I go along a cycle, I will get 0 has to be lower or equal than the sum of the cycle, let's say very formally. This is badly written, but it's the sum across the whole cycle. So basically, this system of restrictions, in order to be satisfiable, we can already see that it can have negative cycles, because it has any negative cycle, it will immediately contradict the implied restriction by adding to the cycle. That if you notice this and you know a lot of algorithms, you say, oh, Bellman fold, I have to check for negative cycles. And then it happens to be enough, right? Because if you use Bellman fold, you can detect if there are negative cycles, and if there are no negative cycles, that is the only limiting factor. There will be a solution if there is no negative cycle. Right? Why? Because as an example, it's actually, well, yes, as an example, you can use the distances computed by Bellman fold. Right? In order, even if the graph is not connected, in order to avoid corner cases, it is convenient to add a new variable and connect it everywhere directly through edges of actually anything would work. Yeah, any numbers will work, but 0 will be the obvious one, right? So this is like having a new variable and many restrictions that say that like each variable minus the new one is lower or equal than 0, which, okay, just make this one big and it will work, or you can do it the other way around. This just has the effect that now it is easy to compute distances. This one. Okay. By the way, in many of these problems, you can do it like subtracting in one direction or in the other direction. And depending on what you're doing, it does matter or it does not, and you have to be careful. So once you do this, if there are no negative cycles, Bellman fold, for example, will compute minimum paths, but you could use any minimum path that works correctly, right? And computes minimum path from this node. For example, you could use float Warshall if you want, it will be correct, right? And if you set by guessing, right? At this point, we're guessing the solution. This will be a common pattern. If by guessing the solution, we set, okay, let's say that the final value of each variable is the length of the minimum path from x to 0, right? The final number that Bellman fold computes. That will satisfy all the equations. Right? Some of you are looking suspicious, like why? But actually, if you look carefully, each equation is actually mentioning triangle inequality. So it has to be true because if they are distances, in the end, if I manage to create a situation where they are actually distances from the start, then they must satisfy the well-known triangle inequality. So if I have an edge like this, and I look at the triangle inequality, this is it. Like its associated restriction is exactly its triangle inequality. Right? If I move this negative x so that it is positive on the other side, I am saying that the distance, the final distance to reach this target j is at most what I can get if I go to ik first and I add this edge. that is true. That is the normal trend in inequalities. Actually, the Bellman algorithm sort of works by trying to use that to improve until it cannot do it anymore. And at the end, since it cannot improve anymore, all of this hold. Another more explicit way to notice that it works. Okay? Any question about this? Yes.
What do you, by adding the extra node on the edges with the weight 0, will all of the other vertices be at distance 0?
No, because they might be at negative distance.
How? I don't understand.
I mean, if all of the LK are non-negative, then every x equal to 0 is a valid and correct solution to the original, so it is not a problem. Okay? So, in a sense, this problem of just find a solution, no restriction, is only interesting if there are negative edges. If all the edges are non-negative, put everything to 0, and this works. And if there are negative edges, well, you cannot use Dijkstra, for example, so it makes sense. Bellman 4 flow is to be one of the more powerful ones. But anyway, you find minimum paths which are well defined if there are no negative cycles, right? That will be the thing that breaks this and no solution. But otherwise, you find well defined distances and they satisfy the equation, so it will work. Right? But yes, there need to be negative numbers for this to be interesting. That's good to know. So in that case, everything will be 0, but it is correct. Basically, that's the thing. Any other question? Okay. This is quite well known. I hope you have used it before. If not, you have one more powerful tool to your disposal. And actually, this is an excellent example of a quite common pattern that will keep appearing today. And it's quite fundamental and magic. So I would like to explicitly mention it. Like 3 steps of, well, magic things have happened. Some are more magical than the other. First, well, we want to maximize. Oh my bad, I forgot. I forgot I was mentioning the maximizing part. Like I could do the 2-step version, but let's do directly the maximizing part. So this actually stems from your question, perhaps. This problem is still somewhat boring because it gives me too much flexibility. Like it allows for any. It would allow for many solutions. Actually, the same algorithm of using the minimum path is not only computing any solution, right? I don't need a different algorithm, but I can notice that this algorithm that I mentioned is computing even more. It's not computing any solution. The solution has extra properties, which are sometimes nice. Basically, the property is that, well, now the starting node has some meaning, right? If I invented it, it is not so useful, but if I did not invent it and it was already there and it's a meaningful variable, then I might care about differences to this x0, right? I might care about, and they might even have restrictions and appear in the input, but I might care about these values, how far away I end up, well, not only far away, but this difference of x, every x minus the x0 as a reference. Right? What is the value compared to this reference x0? An additional property of this problem and system is that clearly if you add a fixed value to all the variables, it still works the same. Right? So that's why it only makes sense to look at differences here. Right? If I wanted to maximize a number, I can add the same, like a million to everything, and everything works and numbers are real. Right? But differences, those I cannot control so much. So let's say I want to maximize this difference, right? Why not? I could have such a problem. There are, for example, one such typical metaphor for that is like, especially for the undirected case, but in the directed case, we could still care about the same. But if this were undirected, I could use a very useful metaphor, which is that I can imagine that every node is like a model sphere, right, that I can hold, and they are joined by string, right, by physical strings, right, and the lengths of the strings are these numbers, right. So if it is undirected, I would have the restriction both ways, basically, right. So when I look at the variables, it will say that the difference both ways has to be lower or equal than the length. So the net effect in this undirected case will be that I am restricted that because of that string joining them, I can pull them apart more than that distance. Right? So I might ask myself, okay, from this x0, right, the sphere of x0, to some other one, if I try to pull them apart as much as I can, but without breaking anything, right, keeping all of the restrictions, how far apart, what is the maximum that's far apart that I can place them, right? I am doing this in 3D, but if I just do it on a line, well, these variables are a single number, right, and the subtraction of the distance. Is it clear what I mean? It's enough, no? So I would be putting numbers in a line, and my restriction would be, okay, the subtraction of those numbers have to be removed such, so it counts the distance. And I might want to choose numbers out that two particular ones are as far apart as I possibly can. Now I will have a problem where I want to maximize something, right? And in this particular problem, and very related to what we have been doing, we can actually, and we have done it if you look carefully already, we have many lower bounds for our solution. What would be some lower bound for, upper bound? I want to maximize, so it would be an upper bound. We have many upper bounds of, I cannot ever put these two more far apart than such a number. Where can I get upper bounds from? In the graph, right? So it has to be a graph. Any path, yes, correctly. Let's say I have this node x, y at some point. For any path in the graph, doesn't have to be a minimum. For any path from x0 to xy, if this is the thing that I want to maximize, just by adding and doing what I have been doing, we can notice that we will get to an explicit bound that tells us, okay, xy minus x0, what I want, is at most, well, the sum along the path. The sum along the path of B itself. B is at most. Right? So I have many upper bounds here. Basically, for any path from x0 to xy, I have an upper bound of that thing that I want to have. So of course, the strictest one, the most useful one, is the minimum upper bound. It's always the case. In a general case, to have many upper bounds, the minimum one is the most useful. And this is the magic step. Here is like the magic couple steps. Magic, no one expected this. Like, there's no reason why that has. Well, there is some reason. We will see later. For some unexpected reason, the minimum upper bound from those we have is achieved with some magical construction. That is usually the case. Construction. Here the magical construction is, if I actually do the min path with Bellman Ford and put the distances in every node from this start, right? Because I want to maximize this distance, but I have to put a full solution. Okay, do the full Bellman for, and the final numbers are the ones that you should use. That satisfies everything, and this will be maximum. Why will it be maximum? Because it actually achieves this minimum bound, because this minimum bound happens to be the minimum path. And because of the way I have magically constructed this, it happens to coincide with the top. Right? Is it clear? So these three steps is why this particular case works. But keep this structure in mind, because it is quite general and quite common. Okay. Any question? Okay, this has the flavor of the general flavor of the kind of problem that we will be looking at. Okay. So, by the way, since we've done this already, and we have this general, quite common pattern of 3 steps, like there's something I want to maximize. So I look for upper bounds, which tell me I will never be able to beat such value. And then I take, well, the strictest of those. Oh, that happens to be the answer. Do you remember any other? This is a bit open question. There might be more than one option. Do you remember other problems that have this property? Or you have never seen anything like this? Sorry? Yes, flows, maximum flow and minimum cut is an actual example of this exact situation. Yes. I want to maximize something, it would be the maximum flow from a starting node to an ending node. So what? Flow, right? And we have many upper bounds. Basically, for any cut, the cut gives an upper bound. I look at the crossing edges, and optimistically I can say, okay, at most all of them are full sending flow, so by the drawing it is very clear I cannot pass ever more than the sum of those edges, which is called the cut capacity. Right? So yes, for any cut, which there are an exponential number, like paths, but for any cut, it is an upper bound, clearly, of any flow. So I have many upper bounds. So the minimum cut would be the most restrictive. And magic, right? All the theory of max flow min cut. It just happens that the minimum of those bounds is achieved. Here, magic is the for Fulkerson method, for example, right? Keep updating. When you cannot, you have a residual network, you look it carefully, you do a lot of combinatorics, you do the drawing and say, oh, they match. I have a flow and a cut that matches. Magic, it was achieved, so the matching is, it was maximum. The matching, not the flow, so the flow was maximum. Okay, that's an excellent observation. This is not by chance. This is all related. Our original problem and flow are extremely connected. And this is an even more general case, right? Like flow is a very specific case of linear programming, right? Linear programming duality in that. So I hope this has motivated the class, the topic of today enough, and this has spiked your interest. I will be happy that it's okay. So then, let's keep this here just in case, but let's move on to another example. Right? Today, we need to do many examples to help motivate this. Okay? And another very interesting example I want to mention is, well, first of all, a simple problem, which we have already used because we have already used much harder versions of this problem, which is the very classic problem of you have, well, at least in competitive programming. Outside of competitive programming, it's not used that much as an example. But you might have many numbers, right, on a row, on an array, and we want the maximum possible sum without choosing 2 consecutive ones. We have already solved a hard version of the problem where we were constrained by how many we used, and I want to know the optimal with 1, with 2, with 3, that was much harder. So let's go back to the simple version, the easy one, right? The one where I don't care how many values I use, I just want the maximum possible sum, right? I think that the most classical algorithm for this is, let's say, everything is numbered from 1 to up to n. And actually, I had one example written here, so let's just use the example I have written here instead of a random. My bad. So this will be the actual example. I think the most classical algorithm is to do some dynamic programming, right? The solution up to and including I, let's say, is just the best among two options. And I take the maximum. I either skip it and not use it, so the same as before, or I choose to use it, so I will use the element, but then I cannot use the previous one, so I skip it. I think this is the one most people will use for this, right? So in this particular case, if these are the values, the values of f, I will just copy them here to think less. But I think if I haven't made a mistake, you can check on the slide. This should make sense. This should be the f values, right? What is the optimal solution for that prefix? So 35 in this particular example should be the final solution, right? But I was this is a real anecdote actually, which only much later, like a few, it's like not too long ago, I ended up connecting everything fully. But just by chance, one of my students, for some reason, solved this problem with a completely different algorithm. That at first I was like, no, that must be wrong, but it was correct in the end, but I was not understanding at all what was going on. So I will write that algorithm here actually. Or perhaps I can actually write it over there so that we can save it for later. Not secrets, this is learning. And hopefully this will all connect and make sense. So the answer, it will basically use two variables, right? The answer and w, some weight or something. If the first number, well, there are equality to b, let's just say these are the x values, just so that the notation matches. Okay. I set it to the first element, and then I go through all the elements, doing some unusual, I don't know what's going on, modification. Right? Something like this. For each other element, do set w to the maximum between 0 and the x minus w. And the answer shall be updated to be increased by w. End of algorithm. This solves the problem. Does anyone understand what's going on here? Because I did not at all the first time I saw it. That was my reaction. But then I did the example and hey, this is magically working. Perhaps it's not incorrect at all. And it ends up being correct. But it's surprising because it looks completely different to the usual. Okay, what's going on? So just as an example, let's use it here. This will be the w values that will be computed by that. So initially it sets just to the first element, and then each one is simply, like it says there, the difference of the next number with the previous one, right? So now I have 5, 6 is 11 minus 5, 15 minus 6 is 9. Then I get 5 minus 9, a negative value, but it happens to saturate at 0, so instead of minus 4 here, it sets to 0. And it keeps going, and 7 minus 0, 7, 7 minus 7, 3. And through the whole algorithm, it keeps accumulating all the w's. So if we add all of this together, we can check that we get to 35, so it works, right? And logically, since both algorithms are the same for prefixes, it holds up to every single prefix, right? This is like the difference between consecutives up here, right? So it is very peculiar, like how this happens to be the case and why does one first think of this and the other one. Okay, at this point we might believe that this works, but it is a bit surprising. And I managed to find an explanation that is more elementary, but this will also be a pattern today. Like we will join into a very powerful theory that some of you already are connecting the dots for sure, because you mentioned that you already had heard and know something of linear programming duality. So of course, that will connect everything. That's in the final point. But we will see this pattern many times. We can use, like, because of the very powerful strong linear duality theorem, these consequences have to happen. And then we have elementary special case magic construction that explain why that happened, right? But there is like a powerful general theorem that immediately tells you, oh, this has to hold. Even if you don't believe it, you can look for the special case-by-case explanation, but this immediately has to hold. It's given to you. That will be the goal. So here I managed to find an elementary explanation in what we did yesterday, I think. My student was basically using equivalent elements. W is the weight of the equivalent element of the whole prefix that we have already processed. If all the time we think, okay, I have a previous W value which is equivalent to all that came before, right? I have already done the replacement. So it's as if the algorithm always thinks that this is on the second step, because even if it is on the 10th step, it already has replaced all of the previous ones with a single equivalent value. So it's as if it's always in step 2, right? So I have a single equivalence value and a new xy value that x sub I value that is appearing. So okay, I basically have two options. I either use the W value, and I will have a solution that looks like this from the outside. I have used this one. I have not used this one, and that is why I can put anything to the right without conflict. Or I might want to use the xy value, then I will not be able to use W. It's as if I have used this big equivalent element, but then I will not be allowed to put anything here, because I have used the equivalent element, right? This is the idea we did yesterday. Now we are doing it on the border, right? Yesterday we were optimizing like the full problem at once, so we basically did that. If this was the optimum, I just do this replacement, but here we are like at every step doing it, so we want to take care of it. And basically this is the check. Whenever this is positive or not negative, in that case it's the same. These more advantages, clearly, I mean, for two elements, the solution is obviously to take the largest one. So that's why the check is whether xy is bigger than w or not, right? Which is the same as saying the subtraction is positive. So if xy is bigger, I will use it. But then the subtraction stems from the fact that in this algorithm we are always accumulating the values. So at every point, we assume that we have already paid the cost of w, right? It's as if we are already using it and counting it from the previous solution. So now we are changing to using this neighbor, and thus the subtraction is what we have to add, right, in order to use it, because we have to stop using this one. And in the other case, we would use a 0 directly, not a negative. We don't want to make the solution worse. So we will take this one. Right? But in any case, in both cases, you can see that for the purposes of what will come later, like not only this is the optimal and corresponds to using the element in the single new equivalent element value, but this new equivalent value leaves a correct situation for whatever we want to do later. Right? I think it is much clearer when this equality holds, like it doesn't saturate to negative. But when it is negative, it means that it was better to actually use W. So then W is better, so we will never use this option because doing a replacement to W will always be best. So we know for sure that we will keep using W, so we know for sure that we won't use this one. So the value that we have to add is 0, we don't have to change anything. And for the future, this will generate no restriction, right? And putting a 0 there, like an equivalent element of 0 to the left, clearly changes nothing, right? So it works. It leaves no restriction to the future. So this explains my students' very smart algorithm. It's just doing equivalent element replacement all the time. Question about it? Okay, so that's why it makes sense that they end up computing the same. But it's highly non-obvious at first sight. So the relation, it's like they are living in two different worlds, these two algorithms. They are thinking about very different things. But they end up computing the same number. Okay? We at least have an intuition of why in this case. Like we know what it is, but it is a very specific. Okay. Okay. Any questions? Okay. And before we have the break, I will actually mention how to solve problem D from yesterday, because problem D from yesterday is the one about the desaparafusadores factory, right? Which is a linear program, very explicitly, right? Problem D connects a lot to today's class. And first, like the way I will explain it now is like this framework elementary way, which is like I magically had an illumination where I find a magic construction out of nowhere, it happens to work, and the proof I will not even do. I will in the air say the intuition, okay, it can be proved exercise, right? Because it's very long and you have to be very careful, but it will be an elementary proof. And the idea that afterwards, after coffee break, we learn the theory, and we will be able to throw a bazooka to this and say, oh, because of the powerful theorem and such, this has to hold. Clearly, this is the solution. It's quite, it is good. Okay. That is our aim. But for now, the elementary, the magic happens way to look at the solution. Which during a contest, if you're not like immediately very familiar with linear programming and duality before, this might be, I don't think you will prove it, but you might guess it, right? And I think I saw the code of some teams and it was almost identical to mine, and I think they had a little bug regarding consecutive elements at the beginning of the cycle, and as far as I was looking, if they fixed the little details, they would have accepted this one like at 3 hours, but I was refreshing all the time, but they couldn't fix it in the content. So that made me very okay, so what is this problem about? We got, ignoring the story, there's a cycle, and we can draw it like this. There is a cycle, and for every, let's say, edge here, right, for every pair of consecutive elements in the cycle, we will have some restriction, right, which is given. So we basically know that this one has to be at least C1, this one has to be at least C2, and so on. When I say this one, it is the sum of the two nodes connected by that edge, which are the actual variables that we care about. Okay. You can change the indices quite a lot. This might be +1, -1, but this is the idea. You have variables in the nodes, and each edge tells you, okay, this one plus this one has to be at least C1. This one plus this one has to be at least C2. And these are all numbers that appeared in the input, right? You were given this value C1, and your goal is to choose the Y values, which have to be non-negative, right? Every single one of them. And these CI values were also non-negative in this case because it's more natural. I think it doesn't need to be, but it is more natural. So everything was non-negative from this number. So clearly there might be a solution, but you want to minimize the sum, right? So we can write it like we want. We are subject to the restriction that basically for each CI, what I said, the variable I minus 1 plus the variable I cyclically, right? Has to be at least this. And subject to the restriction, we want to minimize the sum of the values, right? Makes sense? Is it clear? This was the problem. So put like this, it is a linear program. I still haven't mentioned what is a linear program, but it is for those who know. Things like this are linear programs. And okay, what is the solution? And we want to, well, this one is the reverse, but of course, the same pattern holds for, I want to minimize something, I have many lower bounds, I do magic, and the maximum of the lower bounds achieve the goal. Of course, the same, right, as usual. So I can do, actually, I can find lower bounds here, right, for the thing I would like to minimize. Like I cannot go below this value. I can start trying to find lower bounds. One such lower bound is actually connected to the previous problem, right? Magic is already happening. If I, for any reason, say, okay, let's look at the restriction, but let's look like disjoint independent restrictions, like maybe this restriction and this restriction. If I only choose those two and ignore these variables for now, these two restrictions speak of separate disjoint variables, right? They are a matching in the cycle, basically, if I look at it as a graph. So this one tells me that these two add up to at least C1, and these two add up to at least C4. So since that is a subset of the total sum, I know that my goal will never be less than, in this case, C1 plus C4. Right. By removing these two and only looking at these four numbers, the sum already has to be at the very least C1 plus C4. Is that clear? More generally, of course, I have many of these bounds. I have one of those for any independent matching. Let's say for any matching is destroyed, right? Any choice of pairs of consecutive, which give me restrictions, but not choosing like this one, because I will double count this one, so it's messier. So no, independent, right? So I have many of them. From those, I could take the most strict, right, which would be here the largest, the maximum lower bound, right? What would be the maximum lower bound? It would be the maximum sum of elements where the Ci, which are the input values, are my elements. I can choose in the cycle without choosing two consecutive values. Like, if you were paying attention, that's almost identical to what we just mentioned. We have this algorithm, and it's more complicated, not more complicated. This is more surprising compared to the classic one that we all know. Okay? But I could do the classical that we all know, or that one, it's the same now we know. But this is a cycle, not a path, right, as before. But that is easy to solve, right? I can break the cycle and reduce it to a few cases. Like basically I can say, okay, if I want the maximum sum in the cycle, basically I choose two consecutive of these edges, and I cannot use both. So I consider not using this one, or I consider not using this, right? And once you consider not using one of them, you have the probability path, and so you can do that. You have to do a little adjustment at the beginning and the end, because you have cut the path, but it's two linear dynamic programming, and both can be done actually in constant space. They have the same property. You have to be slightly careful at the edge. I think there was a team that was having a bug, and the only bug was that instead of consider not using this and consider not using this, they were doing consider using this or using this. So see the little difference. That is missing the option, which is sometimes optimal, of not using any of those. That might be better if, like with 3 elements, and the first one, the second one, which are the ones we are looking where to cut, are something, but the other one is like the excellent element we would not want to miss, we miss it. We do not consider them. Okay? So careful about it. But with that in mind, we can efficiently, linear time, constant space, super efficiently, with the classical DP, compute the maximum of this lower bound. Right? So we are in this situation. And we might conjecture, well, I will be lucky and that is the answer actually. That is wrong, but it's close. That is correct when n is even. Exercise. It will follow from the second part of today. Okay? When n is odd, which of course the triangle is the first example that one might study and start finding interesting situations, it's like something interesting happened, which is that so far everything has been integer, even though the problem does not require us to do integer. But for example, if the three numbers were 1, like the maximum bound that we can get this way is 1, so we say, okay, the answer has to be at least 1. So optimistically we say we can achieve 1, but it is impossible to achieve 1 here, right? But if you set all of the values to a half, 0.5, you satisfy the 3 restriction and you get 1.5 total. And that is the optimal solution, right? So just choosing the maximum of this is not enough, but we can add another upper bound, lower bound here, that the solution has to at least be the sum of all the bounds divided by 2. The solution at least has to be the sum of all the c's divided by 2. Right? That is also easy to see if I just add all of the equations, right? If I add all of them, I get twice the sum is twice the sum of the variables. So the sum of the, the sum, without twice, the sum of the inputs is twice the sum of the variables, because in the cycle each one appears twice. So once I divide, that directly says that the thing that I want to minimize, the sum, at least has to be half the sum. So this is another always valid bound, right? And here, 3 divided by 2, 1.5. Oh, here it saves the day. Actually, it happens to be achievable, right? Well, this is the magic part. I'm not proving it right now, but it happens to be a solution. This is now correct. If you include all of these lower bounds, and you take the strictest one, including this extra one apart from the more combinatorial one, let's say, now that will get to the answer. It will give a lower bound that is achieved somewhere. So, because it is achieved, I haven't proved it, but you have to believe it happened. Since it is achieved, okay, it is the correct bound. So with this, you probably now could code, I assume, a linear time algorithm and a constant space. Very efficient, like a few variables, right? By just doing 2 versions of this dynamic programming algorithm, and this is just adding the input. So a consequence of this is that the answer is actually either integer or 0.5, right? So that avoids any precision issues. Just do everything in integer. Okay. The proof, the elementary way to prove this is actually quite long, right? It is hard to find. This is a problem that I invented. I wanted to use it at some contest at some point, but I never, it's like it doesn't fit very well, so I put it here. It fits this lesson very well. And in order to do the full elementary proofs, like you need to, like what you need to do is very unintuitive, because you have to do the magic trick and propose a solution, and then the solution, because you're starting from your lower bounds, is constructed so that it satisfies all your bounds. So it will be clearly optimal if it is valid, which is like the reverse way of the usual way we do most of the proof, right? It's like it will be obviously optimal because it's like you put, for example, if this happens to be the biggest, then you basically set this to equal and solve for this. So because everything is explicitly equal, it has to achieve the lower bound, but maybe it uses negative numbers everywhere. Maybe it is invalid. So now you carefully need to justify why it will be valid. And then you have to use like careful bounds of like alternating sums of these things. And do some reasoning like, okay, these alternating sums have to end up being non-negative because otherwise I can do swap argument exchange and it is not true anymore than this beats this. I would have like a situation where the matching is better, right? So you have to like combine everything. But that is more or less how it is. And that is for this case. When this is the maximum, what you actually want is to put an equal here and use it as your guiding, okay, I have to achieve this bound exactly on those, sorry, not here, but these bounds, now some of these bounds will be equalities. Like you have this one plus this one has to be at least this. Okay, in the optimal solution, some of them will be equalities. And that will give you a system to try to find the solution. Well, the magic step here is, okay, once I have this maximal matching, those that are used in the maximum matching, those are the ones you want to set to be equal, are like the critical ones, right? And then you solve for that, and if it happens to be a valid solution, it will be optimal because you like constructed it to achieve the bound. But why would it be valid? Well, it happens to be valid if this was actually maximum, because you can reason, and it's like if it is not valid, then somewhere I have a negative cycle, and so this problem was not maximum, and so. So that is the general idea, because that way you have a general idea if you want to think about, but it is long. And my main point is that I'm not sure I would have found that elementary long proof on how it looks without doing like cheating, like the other way. I know strong duality, so there is like a theorem that tells me there will be an optimal solution that has to have this form. So now that I know that it has to exist, let's see if there is an elementary proof that it does exist, and well, there is. So, okay. Any questions? This is like a general idea of how the proof would look in an elementary way. I am not proving that. That should be clear. This it's not proved that it is true, but this is true, so this solves the problem. I think this is something that might be conjectured by some teams, and I guess some were conjecturing very similar things, perhaps exactly this. I don't think they have proved it unless they use strong duality. They use strong duality, then I believe it, but the elementary way seems very magical. Well, maybe you can. Yes, I have covered it. And as an extra detail, the proof for this case uses the Bellman-Ford problem that we have mentioned just a moment. Because once you set these equalities, you introduce new variables, and those ones you have to make sure that your original y's are greater or equal than 0, and there are suddenly restrictions like the Bellman-Ford appear, and you have to justify this has a solution. So it amounts to justifying the graph happens to not have negative cycles. And the argument is like if there were a negative cycle, I could do some swap, and this was not actually the maximum. That is how it looks, but it's very complicated. Okay, any more questions? Now you can observe this one. Even more magic is going on. We have more than enough motivation to actually start with linear programming, which would be like how to generalize all of this very motivating example. One extra detail that I would like to mention, we will mention it again in a few moments in the context of linear programming. All of this is convex always because these are linear programs, so it's very important to remember that anything that happens to be linear programs like this will be convex. And so, this particular problem admits a ternary search approach if we fix any variable, right? For example, I could say, well, this problem it could be inspired by what we did before for the cycle solution of the other problem, the one about maximizing the choice without too consecutive. For the original problem from yesterday, I could say, okay, if someone told me how much this variable is, however, I get it, like someone magically helped me with the problem, I am having a little help, and I know, okay, for sure you can assume this one is 2, just because, or anyone. Once you fix one variable, you can solve for all of the rest correctly, right? There is like a greedy approach. I don't know if you thought about it. But that would make the problem much easier if the bounds weren't not so huge actually. Because you can do the internal research on this value I1, right? Because the function, the final function that we are trying to minimize, right, the total cost, will be a convex function. I mean, everything is linear. It will be piecewise linear. This is a linear problem. So there will be an optimal value, and you can do ternary searching. For any of the variables, if you fix it, and then solve optimally for the rest, which in this case it can be done because it's like it breaks the cycle and there is a greedy assignment. Think about it if you haven't. We will do it after the coffee break, that's why I think it during the coffee break. Then it looks like this, and so you can do ternary searching. Right? Find the minimum, actually that's what. But this will take many passes through the input, so no longer constant memory, and L log something time. And this one was intentionally set with very high bounds, so you basically need to find the very efficient form. Right? But with more typical lower constraints, this one could be solved much easier without understanding the details by just noticing, okay, everything's always convex, so I do ternary search, and then some greedy, and I would solve. Okay, that's good to mention. We'll write that greedy right after the okay. So any question before we go right now? Okay, then let's have coffee break, and in 20 minutes we get the theorem. never thought about it, but no matter, we will mention it now. So for this problem that we was seeing just a moment ago, I mentioned that you could actually do interplay search if the restrictions were a little bit more generous, right? This one is requiring a super efficient algorithm, but if n times log something and a few passes for ternary search is okay, you could do some grid. Why? Because of this observation of how things look. And if you fix one of the values, we can do a greedy algorithm. How would it look? Let's say that I guess that this node, this variable, right, the one, the y corresponded to this node, the input, it was the payment of that work, I think, in the story, is 5. I guess that. So I am doing internally and I am evaluating at 5. So what is the optimum when I have fixed this value to be 5? Then I can do some greedy algorithm because if I know that this value is 5, then I can go to the right and say, okay, what am I doing with this value? Well, since this is fixed and I will never move it, now this one can, well, better let's look at this restriction. This restriction needs a sum of at least 10, and this one is fixed to be 5. So between these two, we need at least 10. So now this restriction will mean that this one is at least 5, right? But furthermore, it is very clear that I can just greedily set it to 5, right? I will never want something bigger here. Why? Because this bigger value can help this edge and this edge. But for this edge, a 5 would have been enough. And for this edge, that extra plus 1, instead of using 5, I could have better used at this node, which also helps this edge just the same, but also helps this edge. Well, perhaps that is useful. You see that it's like the edges it is helping is a strictly container set, so it can justify the grid. It is better to use the smallest one possible because the next one would be better except for this edge. So we need at least 5, and the only reason, and anything bigger than 5 does not help this edge, and it would be better to move for the next one. So that is the full greedy algorithm. So then I basically do the difference. 10 minus 5 is 5. This is the new one. 11, for the same reason, 11 minus 5, I would choose a 6 to satisfy that. For this one, 15 minus 6, I will choose 9 to satisfy this one, right? Then here, this one is already satisfied. So by the same logic, well, I don't put negative value here, but I do not want to waste anything there. Better to use it over there, right? So this one now will be a 7, and so on. I have gone the full cycle, and now, because the original problem was cyclic, this would be already a correct linear greedy algorithm if this was actually a path. But because this is the cycle, I will have to check. Did this work? And yes, it basically did work. If it did not work, because all of the choices I made were justified as efficient, then I will basically need to add the missing value. So if this one happened to be a 19, let's say, well, for the guessed value of 5, the optimal would be to increase this 7 right now to satisfy this, right? And that would be the optimal for this guess, right? And then I can do it. Is it clear? So, should we write the code for this greedy? Well, that's very good. Someone is pointing right here, right? We have already written the code for this. It's exactly this, right? So W here is the last black number that I have written, and I just check, okay, let's check the next number, and I do the subtraction, and as long as it is not negative, I put it here. But when it becomes negative, like this, 5 minus 9 goes negative, so no need, I just put 0 and I keep going. And I wanted to minimize the sum of the black values, which is what I am computing, right? So this will be the minimum that I am doing. Which is surprising, because that was a different problem, right? So good observation, those that were pointing there. This is the main motivation. All of these problems are equivalent. We want to understand how to find explicitly the equivalent. Okay? Good. Okay. So now I will finally actually say what is a linear program. It is simple to understand. So now we are moving to the completely general. I mean, it can still be more general because mathematicians study the non-linear case, but okay, the linear case is very, very general, very powerful. We will now finally move to completely general linear programming, right? That's what LC means, linear programming. This programming is a very old word and has nothing to do with computer programming code. It has to do with like choosing the schedule of things and finding the optimal way. So in that way, it is programming what to do. So it's like optimization, right? That's why it's called programming. Even though we also code algorithms for linear programming. Okay? So what is linear programming? Well, it is basically similar in a way to, well, a lot of you already know this, and it is not hard to understand, I think, for you with all that we have seen. This would be the standard problem of linear system of equation solving, which I assume all of you know from university courses or for competitive programming, you might have studied Gaussian elimination, and if not, well, this is a system of equations, right? Where A is a matrix, right? So let's just put some more precision. Let's say B as a vector would live in n, so m real coordinates, right? A would be a real matrix of size m times n, right? So our linear system would have n variables and m equations, right? That is why B is part of the equation, right? This is the linear operator part, and this is like the fixed value. For example, if our equation is like 3x1 plus 2x2 minus 8 x3 equals 24, then for that particular row, for that particular equation, let's say this is the fourth row, right? Then element B sub 4 is 24, right? And the matrix A at the fourth row has value 3, 2, minus 8, right? That is how this works. And here we have more than 4 or more rows, but this example would have, let's say, n equal 3. So 3 variables. So it would have, the matrix would be 3 columns wide. Okay, this is a very standard linear equation setting, right? So general linear equations you can write like this, and you might want to solve. So the x values that we are looking for, they would, as a vector, they would live in r times n. Vectors are like flexible. I can think of them anytime as a horizontal matrix of 1 times n, or as a vertical matrix of n times 1. Sometimes it's only a transposition, right? And so sometimes it's convenient and makes sense to transpose, right? At some point they might have to do it, just keep it in mind. Because sometimes you mix a bit and do like vector and matrices combined operation, and something might have the wrong type if suddenly the dimensions do not match, and it's probably that you missed transposing something at some point. Otherwise it would. Okay, so this would be the linear equation case. So a linear program is the same, but more complicated because we have inequalities, not equalities. So this is usually written like this, schematically, right? So this is a greater or equal. I'm sorry that the standard would be lower. Just keep to a standard. What does it mean? Well, all of this, after doing the multiplication, will be a vector of m values, right? Because for each equation, I will have one of these left-hand side and the corresponding right-hand side, right? So this lower or equal is a pointwise lower or equal, right? Obviously, if I look at it, this is like doing zoom and looking at this expression, but the fourth row only to see what's going on in detail. Okay, I put lower or equal everywhere at each point instead of equal, right? So any system of linear inequalities I can now model like this. Right? If instead of lower or equal, I want greater or equal, there is no loss of generality because I could transform my problem by multiplying all of that row by -1, including B and A, the corresponding row, and multiplying by -1 flips the sign of the operator, so I can put it in this form if I want. Something to notice about that is that I will not have at any point any restriction in general in the signs of elements of A and B, right? Those could be negative. A and B could contain negative elements, no problem. But for the standard linear programming problem, we ask that the solution has to be non-negative. I mean, all this is again points to I, so every coordinate of the solution I want to be non-negative. Right? This is the usual way. And we want to maximize something. What do we want to maximize? Well, a linear function. So for some fixed vector C, the dot product of C with my solution. Again, a dot product, this is again like one single row of matrix multiplication. For example, I would have all of my equations and then a final part that says, I want to maximize 10x1 minus x2 minus x3. And C here will be 10 minus 1 minus 1. Right? C just encodes what is the linear function that I want to maximize. Right? Is it clear what I want to do? This is like the very general setting of a linear programming problem. So this is what is called a linear program. Okay, I think many of you have seen this before. Like I mentioned, there is an algorithm to solve this, actually. It is called simplex. There are other ones. This is the most famous one. The complexity of this one, which is the classic one, is very somewhat tricky, somewhat ill-defined. It's often said that it is cubic in practice. But there are like pathological cases where this is exponential, right? But it doesn't happen in practice, right? You don't find the pathological case that is super, very extremely creative to destroy you. But yes, this is somewhat. You can see that it is a very tricky area. Actually, numerically, it's very tricky to avoid numerical errors. If you can avoid using simple vex or any general solution of linear programming, well, better. Because it is easy to cut bugs, and then you know, is it a numerical error or is it my bad? Who knows? Okay, but luckily, as I promised, we don't need to know about it. We just need to know it exists. Somebody solved this, and there is a way to find a solution and find the optimal solution and actually compute it, and typically it's cubic. Which is similar to Gaussian elimination, right? Which is the algorithm that we would use if these were equalities. Right? This probably has much worse constant and behavior, and it's trickier for numerical, but otherwise similar complexity. Okay, good. So how do we solve this? In general, we will need a very complicated algorithm. This is a generally very difficult problem. So at this, let's mention a special case. And a very remarkable special case is if I have very few variables. Let's say I have at most 2 variables, right? So that I could write everything as equations in terms of only 2 variables, right? x1 and x2, or I could even call them x and y. I have only 2 variables, right? So I will be trying to optimize and maximize something like c1 times x plus c2 times y. Right? I would want to maximize that, and all of my equations would look something like this. So a linear function of x and y, lower or equal that something. How do I solve that problem of maximizing that with all of those restrictions?
Half-plane intersection.
Right, we have seen this in the camp. Andrew gave a lecture last week on half-plane intersection. So that's a very important case to know. If we have only 2 or less variables, we can solve this with half-plane intersection. So we see that the very special n equals 2 case is already like half-plane intersection, which is not trivial algorithm for the general case. So the fully general problem of this is quite complicated and powerful. You can already see it. But yes, and also, I'm not sure Andrew made enough emphasis, but at some point he mentioned, for example, that one of the easy algorithms that eternally and something like focused on keeping the highest point
right? And intersecting things and doing intersectional lines so they become segments, intervals, and everything becomes much easier. And that always keeps like the highest element in the valid region of solution, the restriction, right? Well, of course, there's nothing special about the up direction. We could rotate, and any linear function, the level curves, the level surfaces of this, where the optimizing function has a constant value, would be lines, right? So if I actually look at the normal vector, which is C1, C2, there is a direction in which I want the point most to that direction. So I can either rotate everything at the beginning, or instead of choosing the highest one, choosing the one most in that direction with some calculation. But I could clearly use the same algorithm and get the actual best point in this direction. So Hackman intersection with the ternary nice approach solves linear programming for the special case of n at most. Okay, that's good to know. Is that clear? For n equals 3, you can do something similar, right? It starts becoming more and more complicated, of course, and at some point it's almost like with the general case. Okay, good. So why would we care about a linear program, right? Well, there is a variation of this, which is much more powerful and would be nice if there were a good solution, and would allow us to model almost everything, which is ILP, I guess, that's how it is called, integral linear programming, right? The specific case of integer LP would be the same, but instead of real numbers, everything is constrained to the integers, right? So I would have integers numbers in the input, but I would critically restrict my solution space to be integers. I would want to only have integers in the answer. Okay? That would be integer linear programming. The normal one is with real numbers, right? Unfortunately, integer linear programming is like finding the maximum of almost anything you would want to ask is NP hard. Right? So the general case of integer linear programming we cannot solve, which makes sense because once you start trying to write linear programs with integers, it's extremely powerful. You can model like almost anything with a few equations. Like knapsack is very easy to write in this form. We might do it in a while. So the integer version is very hard. But for the real version, where we are allowed to do things like, okay, I select half of this element and a third of that element, right? Everything has real values. There is a solution, which is nice. But it's worth mentioning that it also makes a lot of sense to ask about the integer version of the problem when we restrict. In general, it is super hard, but it makes sense. Okay. Now, it will be extremely useful to have an analogy for this. So, LP, so we will speak about the factory analogy. I don't know if you have heard it before. To me, it makes everything much easier to understand, especially for what is coming next. So, we will have our matrix A here. So our matrix A our matrix A actually has m rows and columns, as I mentioned, right? So here, as a column, we have the vector B, right, with all of the restrictions. So we can give a story to this system of equations. I mean, we can give lots of stories, but this is the one we will use, and it will be useful in a moment. So one example story is the factory analogy, which we will use to run now. We could say that we have m resources. So this could be wood, metal, gold, whatever things we use to produce products in the factory. We have end products, right? Final products. I don't know, a phone, a book, whatever. Nice products that I can sell for profit. Let's say. So C is actually, well, we know it is a vector, so like this, it looks like a horizontal vector. It makes sense. It will be a horizontal vector of the prices of the products. That is our interpretation, right? And these variables will mean how many units, although in general these are all fractional units, right? So it's better to think of the products as something like I am producing, I don't know, a chemical liquid compound from its components, right? I can fractionally choose any amount of each product, right? But the quantities are so big that one unit is infinitesimal, whatever. But I am in the real case, right? So it makes sense to say I want just a third of a product, right? Keep in mind that all the time. So this C would be the prices of each product, right? So it makes sense that C times X gives me the final profit that I make, right? Or at least the revenue, if I just see how much money I get, right, directly. Because for each variable X that tells me how much I produced of that product, I would multiply it by how its selling price, so my factory would get that, okay? And it allows for negative values, which, okay, it's products that if I produce them, they cost me money, well, for whatever reason, it makes sense. It could be negative. And B, the analogy is to model it as my current net stock of resources in the factory, okay? So, of resource 1, I currently have in stock B1 unit. Of resource 2, I currently have B2 units. So that's why each equation, each row, tells me how much resource I will use in the production, right? So actually, if I look it by columns, matrix A will be telling me how much of each resource the first product uses. So let's say this is the product 1, okay? So the resources are like wood, food, things like that. Normal things one uses to produce products. Then, if numbers are like 2, 3, let's say -1, it means that, okay, per unit of product 1, in order to produce it, I need 2 units of wood that I will consume, I need 3 units of food that I will consume, and there could be negative values if that is the case, like the process of producing the product gives me extra resources for whatever reason. Sometimes they are positive, which is easier to interpret, but no problem with negative. It means that when I produce that unit, I receive units of that. So the restrictions are by rows, because it tells me that across all products that I decided to use, like when I add up all of the wood, let's say the first row would be, okay, 2 units of wood times how much I want to produce of product 1, which would be x1, plus, if here it says 3, product 2 needs 3 units, so okay, plus 3 units of wood per x2, how much I want to produce of product 2, and so on. Each row would count the total amount of wood I have spent, I need to use, right? Or if it ends up being negative, how much I am producing. So I want that to be lower or equal than my stock, so that I can actually do that, right? And this all allows a negative. What I want to do is basically the restriction is that I need to be able to produce and end up without debts of resources, right? I must have, I must owe nobody to no one, right, at the end. So I cannot use more resources that I initially had. But there could be, I could start with negative resources, which is like, from the very start, I already need to get 24 wood because I owe 24 wood to the bank. So I do this process, and this will have to be negative. So the net result will be that I need to be able to produce at least 24 so that I can pay the debt and end up, I can have surplus at the end, but I have to cancel all my initial debt if I had, And if not, if I have stock, okay, I can keep stock or use it all, but I can never end up in negatives, let's say. Right? I have to, if I start with negatives, I have to fix the situation. If not, I cannot go into negative territory of resources. Okay? That is the intuition of this restriction. This is clear. The easiest case is everything positive. Then I actually have that, there will never be any debits anywhere, and I have to use the resources without them running out, and I want to produce the products. Okay? So each restrictions count that I end up with surplus, or zero exactly of that resource. And then my final profit is this C times X, direct. So this analogy models the situation. I want the maximum profit, choosing what to produce, and I am subject to this restriction that I had to end up with surplus in my stock and not zero debt. Okay, even if I started with that. That is what the restriction is. Is it clear? Okay, this is the same as the mathematical model, but I think it helps a lot. It would help understand. This, to me, this analogy is extremely useful to understand, especially what we have now, which is the duality theory. Okay. Yeah, almost at the point where we could state. I think we can actually move to speak about the dual problem. Okay. Any question at all? Okay, let's now create a new problem because we don't have enough problems. This is not hard enough. We need more problems. Okay? So we will speak of something that we will call the dual problem. This dual word, for now, just take it as a name. For no reason, we just call this the dual, but it ends up making sense. So we can invent a dual problem. What is a dual problem? Well, in the factory analogy, right, it is the dual problem of this problem that I have now. The dual problem continues the story, continues the metaphor, and so let's say someone has the factory, right, and has that situation, but now I come from somewhere and I want to buy the whole stock. I want to buy this whole stock B that the factory has, right? So I want like to stop the factory. No, don't produce anything, don't do nothing, but I want to buy everything, right? I want to buy your situation. Even if it is negative, like, that is bad, I would want to buy negative, okay, I accept your debt, you just pay me a compensation, right? But I want to resolve it. So what do I want to do? I want to put an offer, I want to put prices into the resources, because there are no products yet, right? I want to buy the stock of resources, of raw materials that the factory has. So I will be choosing Y values, right? So Y will be a vector that lives here, like B, size M, right? I want to choose a price for every product. And I want it to be in a net. That's part of like the standard math setting that makes everything nice, which is that these X and these Y values are the ones, my variables are the ones that are not net. Okay. The rest could allow net. So that is my goal. I want to put a price to every product. Just like originally in the factory setting, there is a price in the market for every product, right? Well, I want to buy the stock, so I want to put a price into every resource. I want to say, okay, I will say that the price of wood is Y1. The price of food is Y2, and so on. I want to choose prices, okay? What is my goal? My goal is to have, okay, I need, actually my goal will be to pay as little as possible. That will be my goal. So I will be trying to minimize the price I have. But my goal, my restriction, what I need to do is to make sure that they will buy. I have to make them an offer that they can't refuse, right? I need to do that. I want to offer 0 for everything and not pay anything possibly, but I actually need to do the operation, so I will have to do a good offer. So what means, let's formulate, what means a good offer? I want that no matter what they are trying to produce, it has to be a better idea to let me just sell all of the materials to me and not produce them, right? And the materials might be negative, right? And then it means that I end up with the debt that they have, but they pay me compensation. At what price do they pay me compensation? At the same price, right? What I mean is negatives are allowed and you do the same calculation, just the interpretation changes. If the stock was negative, they owe 2 units of wood, so if I say my offer is that wood is worth 5, so if you pay me 10 units, I receive your debt and have no debt anymore, right? That would be like the negative. For positives, it is much more natural. It's just give me your 2 wood, I pay you 10. The same with the sign flip. I can just emphasize the negative. B, A, C can be negatives, there are no problem. X and Y are the negatives. Okay, what do I need to be sure that it is always best to just let me buy everything and not produce? Well, for every product, if I produce 1 unit of this product, for example, the first column, if the factory produces 1 unit of the first product, they will receive C1 profit, right? C1, C is the vector that tells me how much they get for the product, right? So my price has to be better. So let's write it for the first column, basically. I am offering this price for wood, right? So 1 product of type 1 uses 2 units of wood, let's say. Let's use those values. I'm looking at the first one. And it uses 3 units of food. So my price for food is Y2. And it somehow produces gold. So I will receive basically -1 if I do the operation. -1 of the price of that I am pricing gold, and so on. Okay, like this. So this final number for the column is basically what the factory will get if instead of producing actually 1 unit of product 1 and receiving the money, they simply accept my offer and just do nothing and do all the payments and transactions. Maybe if they had a lot of debt, maybe they are paying me a lot, but that is better than having to produce. So for it to be better, this price has to be greater or equal than C1. Right? Otherwise, they would prefer to produce the product instead of using the resources with me as a bank. Right? They would prefer to produce 1 unit and get the money. Right? It's basically which one is bigger. I want to make sure that my offer is good, so I need that no matter what they want to do, it is best to just operate with me and not with the general normal prices. So this is what they will get if they buy everything or sell at my prices. So this has to be greater or equal than the stated price of doing that product. This is clear. This idea ensures that producing product 1 is never a good idea. It is better to cancel that and get to the same net state, which is buying and selling from me, depending on if it was debt or it was surplus of resources, whatever, just buying and selling from me at the prices that I offer. The swap is strictly better. Even for any epsilon of resource, it is better to swap it and operate with me and not produce. And I want the same for every product, right? So it is basically another linear program, but it says greater or equal instead of lower or equal, and it has the columns everywhere, right? So if we actually write it down, the dual has the transposed matrix, right, from the original, because the rows would be like the columns if I have to read it, right? It has, it multiplies everything by y, which is my prices that I have to set, right? And I need to set them so that this is greater than or equal to C, which C was here before. Let's move magic. Okay? Y has to be greater or equal than 0, that is a restriction that we are imposing for similarity also. And Well, what would be actually what I want to minimize? I want to minimize how much I pay, right, to the factory for actually buying the stock, right? And that is basically their stock multiplied, I want to minimize their stock B dot product with my vector of price, right? If they had 3 units of wood and I am buying, then, well, I will have to pay 3 times the price that I have set for wood, whatever it is. If they had a depth of 10 units of something and I say that the fair price is 1, then okay, in compensation, once I have the depth instead of them, I get 10 units, right? That is the calculation of the dot product as before. Is it clear? So this is another problem, and it is called the dual problem. And again, it is another linear program. We could put it into this specific form if we want. To me, it is clearer to when you are speaking, especially when you are using both at the same time. It is more convenient to speak of the primal. When you're working with 2 at the same time, well, the one that you originally considered your problem is known as the primal, and the dual is, well, this one, the other. So the primal is the name for the factory problem, and the dual is the name for this I want to buy the factory secondary dual problem. Okay? So far there are 2 independent problems, but they are connected. Okay. So to me it is clear to keep it like this. This is a maximization problem, and the dual is a minimization problem with the equations the other way around. But of course I could multiply by -1, and now it would become this form, right? So if I want to force it to this form, what I have to do is swap B with C, transpose A, and flip the sign, right? But if I keep that, basically the matrix has been transposed, and very importantly, B with C have been swapped, right? And also the dimension has been exchanged. The primal has n variables and m restrictions. It's like, because of the matrix transposition, it's like it becomes swapped. In the dual, I have m variables because sorry, this is n. I have n restrictions, right? Because I need to beat the C price for every product, but I have m, which were original restrictions of having enough stock. Now I have m variables, right? Because I will set 1 price per resource. Swap. Okay. So why would the dual be useful at all? Any conjecture of why it would be useful? Well, yes, that will be the final, very surprising fact, but that is a very powerful theorem, which will be the conclusion. So yes, wow, surprising. But we will, so let's try to think something that feels more credible, because right now I wouldn't believe it. Like, no, these tools don't have it cannot be the same, okay? Even though in the end there is a theorem that says that the final solution is the value of the solution, right? This maximum and this minimum will end up matching, right? Of course, the solutions themselves look very different because have different dimensions, right? They work on different space, have a different interpretation. That's the most complicated thing here. There is no kind of bijection between x and y, not at all. They are different spaces, they work differently, they are not bijected at all, I will emphasize this a lot. There are relations, but no kind of bijection, and yet the optimal happens to magically align. It's like, I don't know, it's like magic right now, right? Because in a sense it will fit this pattern. But there might be a weaker version, which is, funnily enough, known as the weak duality theorem. This is which you might guess, I mean, or you might be able to prove, like you might see it, you might understand. The analogy you understood very well, you might be able to understand why you can at least do some bounds, even if it's not clear that they will be equal. Okay? That is called weak has some conjecture, like if there's some relation between these values that is clear, at least, if not equality. Right, that would be the equality. Or you mean for every x? The thing is that for every x you cannot use a rule or anything because this has different dimensions. I have n values for x and I have m values for y, so it's very difficult to imagine. So let's actually go to the weak duality theorem. The weak duality theorem says something like, let x be any, and I will emphasize a lot, any here, solution to the primary. Right? When I say solution, I mean it satisfies the constraint. It's a vector of n real variables, non-negative, and it satisfies all the constraints. But no idea if it is maximum. It is one valid solution. Right? It is a vector that lives in this region. Right? By the way, this in both cases, these are half hyperspaces, right, of the n-dimensional or m-dimensional space where x and y live, right? So intersecting half hyperspaces analogous lead to intersecting half plane will lead to a convex region. Right? High dimensional, it is exponentially more complicated to understand and imagine, but it is, in 3D it will be a polyhedron, okay, more or less manageable. In 4 or more dimensions, it is a polytope, which is the same idea, intersect many things, but it becomes like a hypercube would be a very specific example, which you might have thought at some times, and you can see that the number of vertices of a hypercube is already 2 times to the power of n, so the number of vertices of the polytope is exponential as the dimension grows, right? Which is very different to the 2-dimensional case where it is linear, final polygon size of the polygon. So that's why it's simplex. In the general case, it's like it gets out of control. It's good to have that intuition that everything is complex, okay? In both cases. So there will be some polyhedron of region where x can live and it will satisfy everything. So it is like the valid region of the space, right? So when I say that I have any solution, well, I have any point x within that valid region. But from all of those, I will want always to have like the optimal, right? It's like the one that is moved in some direction, but n dimensions, very hard to imagine. So let x be any point, not necessarily optimal, okay? But it satisfies the restriction. And exactly the same for y. Let y now be any, again, solution to the dual problem. So not necessarily the one that minimizes this product, but any valid solution. Okay? So the actual value of the solution using x would be c times x. It explicitly is the value. And the value for the solution using y in the dual would be b times y. This is explicitly the objective function, okay, that they want to know. Do you think that there is any relationship between these two values? I mean, they cannot be equal because these are arbitrary solutions. It's not even optimal, so no chance of equality. It goes in some direction. Let me think. This direction. Okay. This is what the factory is getting as profit, given that they are doing assignment X. So X would tell me how much to produce of any product. Okay, if I produce these amounts of the products, I will get this profit in the factory. And this says, if I put prices Y, which have to be valid, right? And valid intuitively meant that it will for sure be advantageous for the factory to let me just buy everything and not produce. The fair price, I mean the price that given that I have chosen in order to buy the factory these prices, this is what I will pay. Right? Well, intuitively then it makes sense that it has to be like this, because this is something that is possible to get doing this particular way of production, right? But my prices in the dual, why, have to satisfy this. That means no matter how they are producing, product by product, it should be better for them to just let me buy it, right? And that means that that amount that they will get and I will have to pay should be bigger or equal than what they are getting now by producing. Does it make sense? You can actually do the math and it's quite short, but I think that if you do the calculation, you're not, to me, I see at the calculation, I don't understand what's going on. With the analogy, it helps me understand much better why it makes sense. So this is actually a theorem, and it's called the weak duality theorem. Okay, any solution of the primal and any solution of the dual will have this relation, right? When you evaluate their values, for sure, like if you draw them in the number line and compute this objective function value, where for sure for any x you will get something that is for sure to the left of any y solution. Here, this would be like the values, right? So c times x and b times y. Does it make sense, more or less intuitive, this property? For completeness, I will write the proof because it's the easy one, I think. Oh, and it's also useful for something that will come in a moment. To write this nicely, it's useful to introduce what is called slack variables. Okay, let's just put it theoretically. This is impossible to see. Slack variables is new helper variables that are useful for us. That is just the difference between a restriction and the actual value achieved in a solution, right? And they are chosen to be non-negative, right? For example, in the original equation for the main problem, we have something like this. This has to be greater or equal than b. Well, if we invent a helper variable s that is a vector, making sure that it is not negative, we can set the equality, right? Because this had to actually be greater or equal. This one was the other way around. Initially, I have to produce less than or equal to what I have in stock. So if I add some value, I can make it equal. And that value has to be non-negative. Right? It is the same. It's like a helper value. So by definition, S, the slack variable, is simply the restriction minus what I am actually achieving, right? And if it becomes negative, well, the restriction is broken. That's what happens. Those are useful helper values. This has an interpretation. S would be a vector that tells me for every resource, right? Note that S, where does S lives? S lives in the same place as B, right? So S would live here. The slack variables for the dual live here. So S would be my excess resources, right, at the end, which I was saying has to be non-negative. Otherwise, I did not correctly end up without F. Okay. This is simply another way to write. Similarly, for the dual, I will have that I need this to be lower or equal than C. So, greater or equal than C. So if I subtract, I can make it equal. So I will subtract some helper P, and it will have to be equal than 0 to make it exactly equal to C, right? So actually. So the interpretation here is that B, which we leave here, the slack variables for the dual, lives with C, the same place as the prices of the products. B is the difference in price between the vector tells me at each position the difference in price given a proposed assignment of my prices. This is the difference, the net difference that there will be between the price that the factory gets by producing and the price that the factory gets by buying to me, by selling to me. Okay, buying and selling to me. And this has to be non-negative because again I have to set prices so that it's better for them to buy and sell to me and not produce. Okay? So this is just helpful. With that in mind, you can actually write the full proof of the weak duality theorem. So this is the easy one. It fits into this small part of the board and not a very complicated, long mathematical proof. The full proof of the weak duality theorem would be something like this. I have Cx, and this has to be lower or equal than Cx plus the slack variables times y. Why? Because I have added some non-negative value. Y is non-negative, slack variables are non-negative, so clearly I am adding non-negative. Right? It should be immediate. But it is helpful to actually. And then follows a lot of equality. If I just replace, we can say that this is C times X and expand the definition, right, of what was the slack variable. Then I can actually keep going and massage it a little bit, right? And notice that there is X here and X here. I try to join them and distribute. And after doing that, I will basically get. This actually is convenient because we now have matrices and things in different sizes to think of this as column vector. So this is just put the column vector here. This will be column vector 2, and this will be horizontal vector, right? So the dot product is again horizontal versus vertical, it gives a 1 by 1, right? So that the types works, as I mentioned before, and we are doing the correct thing. But anyway, it's just checking that we are not multiplying the wrong one. So by doing that, we get C transpose minus Y transpose A. So the thing is, this should be, because it was a dot product. One way to think as matrices of the dot product is that, okay, I put one horizontal to the left and one vertical to the right, and that gives 1 times 1 actual dot product. If I do it the other way, I end up with big matrix, which was not the dot product. Okay, that's why you have that little detail. So that way I get to this version, where this is multiplied by x, plus b times y. Now we are almost there, actually. If we look at this carefully, this transpose is exactly this thing over here. So this is actually, I am missing, it is this over here transposed, and with the sign flipped. So this is minus the slack variable times x plus b times y. Finally, this is clearly negative because the slack variables were negative, x is negative, this is negative, so this is the full proof. Just arrange the terms that we have lying around. Right? And the interpretation is as we were mentioning before. These terms are a nice interpretation. That's why actually what happens in between, okay, is just glue, but you can believe it from the story. But these terms have a very useful interpretation. Like, sorry, this one, the slack terms multiplied by the actual values. Like, this is if the factory swaps from what it is doing now and starts selling to me, well, all the excess is no, not swaps. If instead of swapping completely, they do what they do now and keep producing, but also sell the excellent, well, this would correspond to the extra profit of selling the excellent, right? And similarly, this would correspond to, given my prices, if I don't do the full operation, but I do at least the cancellation with X, this is the delta in the price. Okay? This is the easiest one to understand. This would be, if they sell the surplus, this is the immediate profit that it will have. Okay? But we already intuitively understood that it had to make sense that this was the case because of the story, because allegedly my prices were played through these restrictions in such a way that any swap of product by selling will improve. So in the end, if you want to do it improve to move from the original solution to one selling nothing, you have to get better values by one specific set of pricing, right? That is not necessarily minimizing. Okay. So that is useful. Yes, this one. Okay, what does it look like? Does this remind you of some other problem, some other situation where you see some of this? I mean, for sure it starts to look like this pattern that we have seen many times before, right? Like we have now we have two related problems because we have a now we're an equal relationship between them, right? So in one problem I am trying to minimize, and in the other I am trying to maximize, but there is a reason why any solution in this one bounds any solution in this one. They are like split, right? So if I look at the maximum of this one, it will be to the left of the minimum in this one, because any pair satisfy that in particular maximum. So there is what is called the duality gap. There would be a gap, but the drawing will always look like this, right? X to the left of Y for the optimal, right? It's when optimal, it will be the maximum, it will be the minimum value, and they shouldn't be flipped, it should be like this. Okay? There is a generalization of this to non-linear problems where this still holds and the weak duality still holds, and there are things like that, but the gap is positive. They don't end up much. Okay? But there is the strong duality theorem that says that in the case of linear programs, the gap equals 0. So this inequality that holds for any pair of solutions, if you actually take the best x and the best y, they match. In that case, they end up matching. And actually, already with the weak duality theorem, it is enough to observe that if somehow we get a solution x and a solution y that match, then necessarily x was optimal and y was optimal, and the values up to if the values match, they are both optimal suddenly, right? Because both bounds tell it so. Like there cannot be a better x because it would be flipped to that y, and there cannot be a better y because it would be flipped. It is exactly like the flow example. The flow and mean cut. Okay? Any flow is lower or equal than any cut, and that already proves that if I find a flow and a cut that match, the flow is matched, the cut is made. But there is a powerful theory that is not random, they will always match. Well, for any linear programs, there is the strong duality theorem, which is hard to prove, but it will work. The idea of the proof, there might be many proofs, but one of the well-known ones, as far as I know, is basically like, okay, if I find one pair of solutions that matches, I am done, I have proved. And in order to find one pair and prove that it exists, I run the simplex algorithm, and so I reason about the algorithm and say, okay, the algorithm works, and it will end up finding a match, so because the algorithm finds the match, the gap is 0. As far as I know, that is basically how most proofs look. But the algorithm is very complicated, and thus the work will prove it. I will not get into this. But it works. Okay? That is good. Okay. So why do you think this could be useful sometimes? useful, especially some examples with the program. I mean, it's not like you thought about program this we will teach you in the first lesson. But this can be used at
You can change like for variables and some restrictions through the other way. I think it can.
right. I mean, I think I get what you mean. It basically gives you a new option of how to look at the problem. Because
It's always useful.
if you have a linear problem and you notice that it is a linear problem, you can say, okay, what does the dual look like? And maybe the dual is easier. And, oh, that's nice. I have a new version of the program and it ends up being easy. Maybe it looks horrible and you say, no, let's get back to the original. Right? But it gives you new ways to think about problems, knowing that the values will match. So you can go to the dual, forget about the linear, and solve the dual. It looks easier in your case. Yeah, that is one very direct, practical way to apply this. Yes?
A while ago, there was a math folder problem, which was like a linear program with many variables and like 2 restrictions. So you took the dual.
It appeared again.
So you took the
I
dual.
have seen that more than once.
Yeah. And it becomes like 2 variables and n restrictions, and you just do not like intersection.
I see. So you will get to practice. Okay. Yes, that is the same idea, but specifically, since it swaps variables and restriction, I mean, if one of those is more helpful, is easier, then you can choose the better. Yeah, that is the most direct way to use it. So we will see that actually there are many examples of this, and a little bit more. I might want to continue with some things to finish this first. So let me see what is the idea to actually do now. Okay, I guess we can at least see that some of our examples are a special case of this. I did not want to. So there are many interesting duality pairs. Let's actually try to look at one such pair right now. Okay. We might have I want to do this one. Let's do the okay. Let's go to let's go with the flow, and we'll continue with the rest. Okay. Let's say we have a graph, right, and we want to do a problem of flows, right? Well, we will actually, because it looks nicer, think about the circulation problem, right? So in the circulation problem, we have edges, and there is no distinguished explicitly right now S and T nodes. So flow is flowing everywhere, right? So there is nowhere that the flow is coming from, nowhere that the flow is reaching, just circulating, right? So at every node, at every vertex, we have the, let me see where it's written down. Okay, here. At every vertex, we have the flow conservation restriction. So for any vertex B, we have that the sum of the flow. Let's say that in the flow problem we have one variable per edge. Right? For every edge we have a variable, right? Let's call them if edge, which tells me how much flow I want to make it go through that edge. So the flow conservation is that flow is not accumulating anywhere or leaving net disappearing from it. It's always circulating. So everything that goes in has to go out. So for every vertex, I look to the outgoing edges from B and sum how much flow goes out and subtract how much flow goes into B, I mean J into B, J out of B, I have to get 0. Okay? And the other restriction of the circulation problem, like in normal flow, is that for every edge there is an associated capacity. I would need the amount of flow I send to be less than or equal to the capacity, right? And actually all of the variables have to be greater or equal to 0. I cannot use negative flow. Right? Okay. So flow, well, circulation, which is almost the same as flow, there is no start and no end. The restrictions of what is a valid circulation, which is very similar to flow, is actually a linear program. Do you see that? There is a detail that might we have not mentioned, but it's here lurking around, which is that we have equality here. And our standard formulation uses all lower or equal than something. Right? Okay, let's say that I want to keep it in the standard form to make it to keep the reasoning exactly as we have been doing. A trick that will always work, so this example will show the general pattern, remember it, is that I can invent like, well, for the restrictions I can simply change it to 2 lower or equal restrictions, right? So I can imagine that this equality actually leads to 2 restrictions in the true version of this. So if I have rho is equal to 0, like this, what I am actually writing is rho is lower or equal than 0 and minus rho is lower or equal to 0. Right? And that will be equal. So this is what I actually have. So these are 2 restrictions. Okay. So this is our primary. Well, I am missing the objective function. And here the interesting thing, you can start thinking about different objective functions with the same basic restriction, which is the circulation problem, and you will arrive at many pairs of interesting problems that are not obviously equal at all. It's a nice exercise. I fully recommend to do it, especially if you are a problem setter. This is a machine of inventing crazy problems. So, if I want to use circulation for flow, I can actually now choose one specific edge, which goes from T to S, right? And say, oh, okay, actually this edge, let's say I wanted to solve maximum flow. Actually this edge is the special one that has a very large capacity. And my goal function is that the flow I want to maximize, the flow that goes through that particular edge, the flow from T to S. So if I ignore this edge, like anything that I send from T to S has to end up circulating for the situation to work, so the rest of the graph has to be flowing that back from S to T. And I want this to be maximum and no restrictions, so this would model the max flow problem. Right? Circulation is more general, you can put other weights and model different things. This particular choice of this is what I want to maximize and this has infinite capacity leads to exactly max flow from it. And the linear model in this way is much nicer because S and T are not special. You have conservation flow everywhere. Not to raise nodes that do not conserve. Okay. So we can build the dual as an exercise here and see what we get. Right? So what would we have in the dual? We have to think that we have to remember that rows become columns and columns become rows. So for every variable here, we will have a restriction in the dual. For every restriction here, we will have a variable. Right? And also, all of the restrictions, like the capacities and these zeros, have to become, well, these zeros have to become part of the objective function in the dual, and the coefficients of the objective function, which here are all 0 except for this particular edge, which is 1. Right? This is a linear function of the variables, which is 1 per edge, telling me how much to flow. This will be like 0 times this, 0 times this, plus the only one that I care about, which is this one. So those will become the numbers on the right of the rest. Okay, so we can think about that. Because we have two restrictions like this, actually, just to do it like mechanically, as we have been doing, I will have to introduce two variables, right? One for the lower or equal, for the positive and for the negative case of this one. And I have one of these restrictions per node, right? Because flow conservation is per node. So I will have two variables per node, right? I will call them. So the variables, those I will call the positive one of node I, will be this, and the negative one of node I, it will be this. This is just notation. And then, because I have one restriction per edge with the capacity, that will become one variable per edge. And here, well, I will call it the variable of that particular edge. That's how it works. So all of those are the variables in the code. And what do the equations look like? Well, I need to have one equation, one restriction per original variable. But I have one variable per edge in the primary. So I have exactly one restriction per edge in the dual. And what does it look like? Well, I need to, for every edge, which will be, look at its restriction, right? I want to see what are the restrictions in that one. Sorry. Since I want to write the restrictions, there's one per variable. So for every variable in the original, so every edge, I have to look everywhere. This would be like looking per columns, everywhere for that variable, in what restrictions it appears. And there are like two kinds of restrictions, the vertex one and the edge ones. And for each of those, where it appears, I have a term in the corresponding restriction of the edge. But any particular edge appears few times in the primary. In this kind of conservation restrictions, it appears like once because it says this edge from I to j appears adding to the outflow of I. And it appears subtracting to the inflow of j. And nowhere else in this restriction. I mean, it will appear 4 times because of the duplication. Nothing else. And then this variable also appears once, exactly once, in its own capacity restriction. So we will have 5 terms in total per edge in the dual, the restriction. Right? So each edge, the corresponding variable appears in the equation for j and in the equation of if the edge goes from I to j, it appears once in the equation from a, I with one sign, and y with the equation of j with the other sign. So the final thing you get is equations like it appears in I adding, and it appears in j subtracting, but then these are equalities, so they were duplicated with the opposite sign, and that would be the other variable that we're introducing. So this is also subtracting with the negating one, and so this is subtracting the, so if this is subtracting, this one is adding, it's the other way around. So we can write it like this. So this duplication is because of this duplicate to get the equal, right? So this is actually what we get as the dual because of all of this. And there's one more appearance variable for every edge, which is in its capacity restriction, right? There it appears with coefficient 1, so this will simply do one more plus the edge variable, right? Because these were associated with this restriction. So it's hard to think because everything is swapped. Restrictions become variables and variables become restrictions. It's just following the arrows and this is mechanical. I mean, you could write the full matrix, but here it is extremely sparse, so it's faster to see for each restriction, put a variable. For each variable, check where it is, and list every appearance, and you get the final equation. And this has to be greater than or equal to the corresponding cost in the objective function because costs are swapped with the capacity. B and C are exchanged when taken duality. So these ones are almost all 0, basically. So this is 0 for almost every edge, but it is 1 for the specific edge from T to S. Right? This is our model of the circulation of mass. Right? So almost all of the equations look like this, but the particular one from T to S has a 1. Okay? And this is a general pattern that you might notice. Well, we also would like to know the objective function. So this is a minimization problem because it is the dual, right? So what is the minimization problem here? I have to look at what originally was B, the restrictions. The objective function becomes the numbers in the restrictions. The numbers in the restrictions become the coefficient of the objective function. So these zeros are very convenient because they mean that the vertex variables do not appear at all in the objective function. They are multiplied by 0, right? So these restrictions, which have non-zero B values, are the one that corresponds to these E variables here. So that those do matter, right? So for each restriction corresponding to an edge, so this restriction will be the restriction for edge ij, let's say, by what originally was the capacity multiplied by how much I am using of this variable that I don't know yet what it means, because the dual is very different. It's no longer flow. It's something else. So this is what I want to minimize. So now it is like capacities became costs of the values in the edges. Right? In the factory analogies, it was explicit. They are priced here. What am I pricing? It's like I am putting a price to the capacity of the edge. Basically, that is the analogy. Okay, so this is the full dual problem. And there is a pattern that you can actually skip to make this faster, but I wanted to show it. This will always happen. When you have an equality restriction, you can model it mechanically like I did with two inequalities, and then you get two separate values because of the duplication. But because they are matching always in pairs with opposite sign, every time that these duplicated variables appear, they will always appear like this in a subtraction, right? So I can rename it, right? I can actually introduce a function phi and say, okay, let's rename it. In this case, it makes sense to rename it and say that phi I is the adding one minus the subtracting. And then it only appears in terms of phi. Right? Even here, it would have appeared in terms of phi, but in this case, it happens to be 0. So then we can rewrite this in terms of phi, and that's it. So we only care about the difference between those two variables. Like it is redundant. 3, 3 or 0, 0 would be the same, right? The only thing that ends up appearing anywhere is always the subtraction. This should be J, right? This one was like the other. So this is a general pattern. Actually, if you do duality and you allow for equalities, the dual of an equality becomes an unrestricted variable, right? Because originally we always ask that variables are not negative, but if we have a subtraction of two non-negatives that are arbitrary, and it is our new variable, now this one lives in the negatives too. This one is unconstrained. It can be positive or negative. But that is a very fun detail. An unconstrained variable in the dual becomes an equality restriction, and an equality restriction in the dual becomes an unrestricted variable. It's surprising, but it still matches the pattern thing that everything translates nicely. Okay, so we have this new crazy problem. It has a lot of restrictions about some phi, which is any number we want per node, and it never appears in the cost function. So basically, we have to set values of E such that this has a solution with the phi's as variables that I can set at any time per node, such that for the chosen E, this is minimized. Okay? And this restriction have a very specific form that we have seen before. Do you notice it? We have one variable per node, phi of I, and it is always a subtraction of two of those. But in this case, lower or equal to 0. But if I move this, let's call this number here B, which is almost always, let's call it, this would be like the outflow from node B originally, which I am saying that it is always 0. So let's just sorry, this would be like the difference. No, this number 0 comes from the initial objective function. So this one here is the only case when it is non-zero. So this would be the original costs, benefits per edge. I don't know, let's call it the benefit of the edge. This 0 here is the benefit of the edge from I to j, which here it is almost always 0, but for the edge ts we care about. Right? So in general, the equations here all, if I put it into lower or equal form and move a little bit, they all look like phi j minus phi I, lower or equal than, and this is now on the right, the variable that I can control on that edge, minus the what was originally a benefit multiplier for that edge, how much I am interested, which is almost always 0, but it's a little one modifying for the important critical TS edge. Okay. And there is one capacity that no, the capacities are here, it's just that one of those is infinite. The TS is infinite here, but it is there in the objective. Okay, and this has the Bellman-Ford nice algorithm to solve and check if there is solution we have mentioned before. We will never have to run Bellman-Ford here, although you might be, if you think about algorithms that have this phi notation and use things like Bellman-Ford, and these are called potentials, you may have seen algorithms like that. It makes sense because actually these are the potentials that appear in the dual when you do this. They are not random phi, they appear from doing this. But if we look at it by itself, once we fix the values of E, we will have fixed values per edge, right? And then this has a solution if and only if there is no negative side. We already know. Right? And since the phi do not appear in the objective function, we do not care what they are. What we care about is that there is no side, right? And then there will be such. So this is extremely interesting. By doing this duality, the net effect that all of these constraints have, so that once we fix the E values of our variables, so that some phi exists that works, is that this says the graph with these weights over here has no negative sides. So that is the dual problem, is I want to minimize this calculation, so I can use these extra variables per edge, but each one has a cost. And what I need is that the final graph that has these weights has no negative side. Well, what is that graph? Well, it has the same edges as the original. All of the edges are the one that appeared in the original. That hasn't changed. The weights have changed somehow. These E are the variable that I can control. So if I set them all to 0, this would be all zeros except one particular one that is -1, which is the T backwards edge. So all of these edges is as if they are 0 now. All of the edges are 0 now, but for each edge, I have a variable that allows me to increase the number in that edge. Always increase because it has to be non-negative. Right? So this is the dual problem. I am interpreting it. The dual problem literally says you have to choose per variable, per edge, one variable which has to be non-negative, so you will add it to the current value, and the current value is all zeros except this one that has a -1. And this one you choose the one. For this to be able to have a solution, the result must have no negative side. That is the dual problem, the dual restriction. And from all of the ways to do that, for each edge, there is a cost of what you are paying to do this addition to the edge. And you want to minimize that. And those costs are the original capacities. So if this edge originally had a capacity C of that edge, that is the cost per unit. If I want to increase this 0 to 7, I need to pay 7 times the capacity, and so on for it. And this one had infinite capacity. So this one, I cannot increase. If I increase it by epsilon, I pay infinite. So not increasing it, setting its variable to 0, it will be the optimal, so that I don't have to pay the infinite. So this one is fixed. This -1 I cannot change. But I need to add to the other ones to remove all the negative cycles. But this is the only negative value. So any negative cycle that is here is necessarily some path from S to T in the graph without this edge. And that one is currently at -1. So for every path, I must add at least 1 through all the edges of the path. Does that remind you to some problem? That is exactly min-cut in the continuous version, right? Because we are always doing this in the reals. The theorem holds in the reals, right? The theorem, this is very important, does not hold for integral linear programming, right? For integral linear programming, because you are restricting more, you might have a gap, right? I mean, the place where the optimum matches might be at non-integers. So if you restrict the problem to integers, you will get a worse solution than in general. You are restricted. So maybe the x gets rounded somewhere and the y gets rounded somewhere. So there might be an actual gap between the problem and the dual in the integer version. Okay, that makes sense from the drawing, and it can happen. So equality, this is extremely important. Equality is not guaranteed in the integral case, which we should suspect because I told you it was NP hard, very powerful. And otherwise we will have polynomial algorithms. Simplex is not polynomial in the worst case, but there are unusual algorithms that are polynomial in the worst case. So linear programming is solved in polynomial time, that is not. So since we think P is not equal to P, probably this could not hold in general. But we already get that the continuous version of min-cut, which is I cut half this edge, I cut a third of this edge, I can choose how much to cut. Okay, a cut works if for any path you have in total in that path at least cut 1 edge, right? You can cut 2 edges half, or you can cut 1 edge fully. Right? If we restrict it to integers so that I can cut 0 or 1 an edge, or bigger than 1, but in this case it is clear that it makes no sense to that, then this would be exactly the normal min-cut problem. Okay. So this is extremely interesting, right? So this looks like min-cut, but the continuous version. So by strong duality, we know that the continuous min-cut exactly matches the max flow. We have like the continuous version of max flow min-cut proved just by applying and seeing what we get in the network flow from the general super powerful linear programming strong duality theory. Okay. So you see the pattern? You can get many other problems by changing this cost nicely. There is, for example, you can think of what is the dual of minimum path, and that is related to this. I want to get it as far as possible, so I want to minimize the path. It becomes in the dual something like I want to put these 2 points as far as possible, but I am restricted. I cannot push and break the lines. Right? So there are many of those that you can find by just playing with this. So I encourage you to play with this now. And then on Thursday I will add a few extra things because we should be finishing now, which will also help us in solving some specific problems, like problem D from yesterday, like this. It already helps a lot because you can try that as an example. See, problem D from yesterday was a dual problem. What do you get? Sorry, it was a linear problem, direct. What do you get if you go to the dual? And the dual is actually much easier, right? In that case, so that's. I encourage you to think of problem D by using this. Like you just write the dual down and you will see, oh, this one is much nicer than the other one, right? And actually you can, just by that I think you have much more chances of solving it because it is easy. It is subjective, but they are equivalent. To me, it's clearly easier, the dual problem. And also on Friday, I think, the next class, we will mention a few more. And also we will see some common and well-known examples of when and why, which you might have seen already if you did linear programming course in university. But sometimes there are some cases where the integral linear program and the real valued linear program match, right? And there is no gap in the integral, and you are guaranteed that the optimum will be found at some integer, right? If we remember the geometrical intuition that allows us to use, for example, at the intersection in 2D, in general, this is like a complicated polytope in multiple dimensions, but because everything is linear, the optimum should be at some vertex of that polytope. That is basically the simplest algorithm. In an intelligent way, move through the vertices until you cannot improve, and then you are at the best vertex. But move through the vertices of the polytope is complicated. There are some conditions under which the vertices are guaranteed to be at integers. So there are optimums at integers. For now, it is well known, so actually I know what you're supposed to prove, we will mention in extra class, but I haven't done the calculation, but someone has done it. For this problem, like for this matrix and this situation, for a problem that uses the coefficients of the circulation problem, the vertices are always as integer position. So now, if we believe that, then we have proved have to know, okay, the immediate consequence is the continuous version. Here, we also have extra conditions which allow us to deduce there will be an optimum in integer coefficients, and then when you look what this means for only integer solutions, then this becomes the normal. Approved. Not from me, that field. But basically, in all of the examples where you can go back and try to check yourself, that would be a nice exercise. In all of the examples where I showed some problem and then magically the same solution appeared unexpectedly, now we have an explanation. If we go and check the coefficients, what was happening in all of those cases is that the problem that ended up matching the other one unexpectedly, well, they were duals, right? And that is why they end up with the same solution. So they look different. They are exactly the same. For example, the initial example of maximum elements without two consecutive maximum sum that I did, that my student had a totally different algorithm that we have written here. Well, my student's algorithm matches exactly the natural 3D algorithm that we would do in the dual problem. So that connects them two beautiful. In the dual problem, you would naturally think of this grid. And this is a code that if I told you the dual problem, you would think fast. But for the original, you would think, well, the relationship is that they are dual. That's why they end up being the same. Okay? So that's almost all, but the remaining things, I will mention them on Friday. This is more than enough. Any question? Last question about any of this? It's easy to get lost in the notation for this, I know, because it is like the general things of coefficients and matrices, like everything is very general. But I think these are very nice ideas. It is worth to try to gain practice by starting to experiment and dualizing everything, right? What linear programs do I know? Okay, let's check the dual. And it might be horrible, but sometimes you find some gems like this, for example. Okay, that's all for today.